Hey there everybody, my name is Chris Brady and this is going to be my second video for the EMAG 303 extra credit assignment. You guys may have just watched my previous video. I'm going to take the results from the last video and we're going to apply them to MATLAB to see what stresses and strains we come up with for that wire that was being investigated. So we're going to start with the clear CLC to get rid of any previous inputs or calculations that were done on MATLAB. And then we're going to supply MATLAB with the given values that were determined or given to us in the last part. So we got a length of cord being 7 meters, diameter of 0.0127 meters, and then we get a force applied from the two hay bales of 490.5 newtons, an elastic modulus of 200 gigapascals, which is 200 times e to the 9th, or 200 times 10 to the 9th gigapascals. Then we get rho, which is a given for steel of 2,700 kilograms per meter cubed. The gravitational constant, which is 9.81 meters per second squared. And then since we're not working on paper anymore, we are going to get a little more complex and use a greater number of nodes and elements than we did on the paper portion. So that n is representative of the number of nodes, and this ne is representative of the number of elements. So there is one less element than there is nodes. So we're going to do 10 nodes in this example with 9 elements. So now we're going to define the y coordinates of the nodes. Since this is a vertically hanging cable, every node is going to have a y coordinate. So we're going to start like so. Y equals length space. And then we're going to go from 0 to the length of the cable n times. So from 0 to 7 meters, we have 10 nodes equally spaced. So now we can define the cross-sectional area, which was discussed previously as well. So that's pi times r squared. So that's the diameter divided by 2 squared. And then from here we can also determine the volume of cable. So this is going to vary depending on the node being examined. So it's going to be dependent on two y points, y1 and y2. And then the volume is the cross-sectional area multiplied by the difference between those two y points, which is the length of the cable being inspected at that moment to determine the volume of it. And then we can also define the stiffness of the elements, because this is constant throughout. So this will remain the same for all ith nodes from 1 to the ne, the final node. And it's going to be spring stiffness equals cross-sectional area times the elastic modulus divided by the length. Then we're going to end that loop. And then we are going to define the loading at each node. So the loading at the ith node. So we're going to start by defining the load as zeros initially at all points. And then for I equals 2 or 1 to n minus 1. And the reason we are going from 1 to n minus 1 is because we know the weight applied at ne, which is the final node, and that is equal to just the weight applied from the bales. But the rest of it is from the weight of the cable itself, which can be determined using rho, which is the density, times the gravitational constant, times the volume, which we just discussed as being a function of two different y points. Then we'll end that. And then, as I just stated, we know that at the nth node, the final node, the force is just equal to the force applied by the two hay bales. So now at this point, we can create the matrices that are needed. So ultimately we're trying to solve for the U matrix, which is the displacement of the nodes. So we're going to create the M and B matrices. So the M matrix is going to have n rows and n columns. So, like so. And then the B matrix is going to have n rows, but it's only one column, so it'll be n by 1. And now we'll be able to apply the pattern that we found in the previous part for the interior nodes. So we're going to loop over interior nodes. We're going to say for I equals 2 to n minus 1, because these are just for the interior nodes once again. So along the diagonal, we have this being the function. Then to the left of the diagonal, we have this. To the right of the diagonal in the M matrix, we have this. And then we also know what's happening in the B matrix at the ith node, on the interior. And this is just going to be the weight at each node, or the loading faced by the node. Then we also determined that there was a known pattern for the first row of the matrix, which corresponds to the first node. So this can be utilized as well as this. And then we also notice a pattern for the last element, which is the last row in the matrix. So the M matrix of the last node is as follows. That's along the diagonal. And then to the left of the diagonal, this pattern holds true. And in the B matrix, this is true. So finally, now that we have the M and B matrices made, we can solve for displacements. And solving for displacements means solving the U matrix, which will be the inverse of the M matrix, multiplied by the B matrix. And then now at this point, we'll be able to plot the solutions. So we will plot solutions. We're going to start by plotting the undeformed location of the nodes, just as a reference for the strain calculations. So we're going to redefine the y-length space, because we need to transpose it so that it can be properly matched with the data points. So it's going to be from 0 to 7 n nodes, and then transposed. And then this will be figure 1. And we're going to want to make sure figure 1 is cleared before we do this. And we're going to plot the y position plus the previously calculated deformation and then we will give it a title so we know what we're looking at. Then we'll be able to move on and be able to count the strain for each element. And then the strain for the I of 1 to any, so the number of elements. So the strain is equal to the difference between the displacements of 2 points. And then we're going to put this into figure 2. We're going to plot the strain with dots. We're going to label the x-axis so we know what we're looking at. The x-axis will be the element, and then the y-axis will be the strain. And then we're going to give it a title so we know what we're looking at. So this will be the node strain graph. And then lastly, we are going to also graph the stress. So the stress of an element is equal to the elastic modulus times the strain. This will go in figure 3. Let's make sure figure 3 is cleared. We're going to plot the stress with dots. And then the x label will remain as element. The y-axis will now represent the stress faced by the element. And the title, so we know what we're looking at, will be node stress. So now we're ready to see if our results were reasonable. So again, error in line 65. And it's because I didn't use an O there. And then I also have a mistake in line 82 because I didn't say Y label. And now we have all our results. So here in figure 1 we can see the undeformed node positions all at their datum along 0. Then we have the strain, which is showing that element 1 is experiencing the most strain, and then that's decreasing as we go down the bar. And then the stress follows an equal pattern, as the further the element is down the cable, the less stress it faces.